Biochemists, we're going to keep talking about carboxylic acid derivatives, and today we're going to look at esters and anhydrides. Anhydrides are almost as reactive as acid chlorides, a little bit less, but a little bit more reactive than an ester. Remember, an ester is a carbonyl flanked by a carbon on one side and an alkoxy group on the other side. An anhydride kind of looks like a double ester. It's two carbonyls flanking a single oxygen. Their chemistry is similar, so we're going to lump them into one lesson here. As we did with the last time, we're going to start by just recapping some reactions that we have already learned, or maybe a few new ones, and then we'll do a few mechanisms. So first off, to turn an ester into an alcohol, we can use lithium aluminum hydride. We've actually learned that in Orgo 1. Same as what we learned with acid chlorides. If you want to make a tertiary alcohol out of it, you use a Grignard or a lithiate. It adds twice, just like what we saw with acid chlorides. If you want to make it into an aldehyde, you can use the new reagent from the previous lesson, T-Butyl, diisobutyl aluminum hydride. We'll stop at the aldehyde. Going back to our first lesson in this unit, we learned about making carboxylic acids with saponification. That's base followed by acid. We'll actually review that mechanism today. Alternatively, you can just use aqueous acid. We call this hydrolysis. Almost any carboxylic acid derivative can convert itself into the acid with acidic water under hydrolysis conditions. To turn acid into an anhydride, you use a carboxylic acid. Acids are not reactive enough to just link with each other. That's a dehydration, so either heat it up or use an acid catalyst. We'll see that mechanism as well. Below that, we have the conversion of an ester into a different ester. I'll call it R1 and R2. You swap them out with just a different alcohol, R2OH, and that's called trans-esterification. That's actually also under acidic conditions. Off to the right, we have two reactions of anhydrides. You can split it apart into an acid and an ester by using an alcohol under acidic conditions. It's a little bit tricky to figure out which one adopts the R group. We can get into a problem with that later. Or you can cleave them into two carboxylic acids, essentially the reverse of this reaction over here, by using acidic water. Again, that's hydrolysis, same as what we saw up here. So now let's look at a few mechanisms that apply these and some others. Starting with the reaction of a cyclic anhydride into what looks like a cyclic double amide. This is actually called an imide, but it will illustrate how things like anhydrides react. This is under acidic conditions. So remember, for acid catalyzed mechanisms, the first part is something that picks up a proton, you have positive charges along the way, and your last step is to lose a proton. Now, the nucleophilic part of a carboxylic acid derivative is the carbonyl carbon. So my first intermediate that I'm going to draw is simply carbonyl picks up an H+, and you get an oxonium with a plus charge on that oxygen. Next up, we have ammonia that will act as a nucleophile and attack that oxonium carbon, sending that pi bond up to the oxygen. We're still cyclic here. And those first two steps we should have been able to do without even looking at the product yet. We know that to activate something, the more nucleophilic spot of all of these acid derivatives is the carbonyl oxygen. Remember why? Because the lone pairs on the neighboring group, in this case the oxygen, are tied up in resonance. In fact, if you think about this resonance contributor, it shows how electron-rich that oxygen is compared to the one that's just singly bonded in the structure. Then we have a nucleophilic nitrogen, the lone pair attacks, and you get to this intermediate. Now let's look at the product up above, this imide, this cyclic imide, and ask ourselves, what do we need to lose in order to get from this intermediate in a couple of steps to that product? Well, we need to cyclize somehow and get that nitrogen in the ring. That must mean I need to open this existing 5-member ring up before I ring close it back. If you also just look at this and try to balance the overall reaction, we've lost the net equivalent of water. So say plus H2O over here on the right. That's going to help us figure out certain steps we need to include in our mechanism. So how could we open this ring up? Well, we can't do it now. If I brought these electrons down from this oxygen and opened this ring, you would get a negative charge. No way. Not under acidic conditions. So a good idea, anytime you're stuck in these mechanisms, is just try an H transfer. That's just our abbreviated removing of a proton from one spot where there's a plus charge and putting it back on another spot where you have an atom with lone pairs. I'm going to show it in one step from the most nucleophilic spot, this carbonyl oxygen, taking one of those extra H's on the nitrogen will actually break a little NH bond and neutralize the nitrogen. This is an acid-base step, so it's very fast and highly reversible. Our job is to figure out what gets us to the product. So now we have a positive charge on that carbonyl oxygen down below. Now we can open up the ring. If I bring a pair of electrons down, frankly from either the oxygen or the nitrogen, those are both okay, you can then open this up and send that pair of electrons to form a pi bond and neutralize that recently positively charged oxygen. Now our ring is open. We have an oxonium carbon with a plus charge on that, and then what looks like a carboxylic acid down below. So now again, let's look at our product up above and say, well, how do we get there? We need to reclose this ring where the nitrogen is the linkage between the two carbons of the entire ring. Again, it can't attack now. Even though it's a nucleophilic nitrogen, you're not going to have this kind of arrow pushing because you would have a negative charge. So let's do another proton transfer. Now that the ring is open, let's get it off of that oxygen up at the top and put it on the carbonyl oxygen down below. In all likelihood, this happens in 2 separate steps, so you get to a neutral intermediate. We are abbreviating it here just in the interest of space and time because they are fast and reversible. So now there's an extra H down there, plus charge on that oxygen. Now we're ready to close the ring. Draw an arrow from the nitrogen to that carbonyl carbon, or oxonium carbon. Send those electrons up. So far so good. We've never gotten a negative charge anywhere in our mechanism. Plus charge now on the nitrogen. So how do we finish up? Well, we still need to lose a water molecule. That's why we balanced the reaction a moment ago. I don't have a water molecule. I have 2 hydroxyls down below, but turn one into a water molecule with, yet again, an H transfer. So let's draw an arrow from one of the oxygens to one of those extra H's on the nitrogen, stabilizing that plus charge. I'm just going to draw this continuing up here. Now we have a water molecule, OH2, attached to that carbon. Water molecules are a great leaving group. Great leaving groups leave. So draw an arrow showing that leaving group leaving. At the same time, you can actually bring a pair of electrons down from that neighboring oxygen. We're going to get to an intermediate that looks a lot like the product. So all that's left is to remove that H+. We started by putting an H+ on. We lastly take one off. I'm going to use the water molecule that we just made. And that gets you to your imide. Regenerate your acid catalyst. Okay, so new reaction actually to make an imide, looks like a double amide, from an anhydride under acidic conditions with an amine. There's 2 other mechanisms on here I want you to try. The first one is a saponification. We actually have seen this before, but I want you to try it again. This is intramolecular. You open up this lactone, this cyclic ester, to make an alcohol and an acid. And then a special reaction at the end that turns the carboxylic acid into a T-Butyl ester. Try both of those, hit pause, and then come back and see how you did. Okay, let's see how you did. So in the saponification, the first part is nucleophilic attack of the hydroxide to the ester carbon. We are in base for the first part of this, so I'm thinking I should only have negative charges. You'll get an intermediate with an OH and an O negative that used to be the carbonyl. Then this oxygen anion comes back, reforms the carbonyl, breaks this carbon-oxygen bond. You get a negative charge on that oxygen down there. Now you might think you're just one step away from the product. I should just throw in the H+, and then I would get right to that. Yes? Actually, no. Before you ever throw in that H+, as a second step, something very fast happens, much more quickly. And that's an intramolecular acid base. You have carboxylic acid and an alkoxide in the same molecule. You're going to do an acid-base reaction, turn that into an alcohol and a carboxylate, which will look this, with a negative charge on one of the carboxylate oxygens. Go back to the very beginning of Orgo 1 and explain why that is. pKa of an acid is about 5, but the pKa of an alcohol is about 16. And acid-base equilibria lie on the side of the weaker acid, which in this case is the alcohol. Or look at the stability of the anion. Resonance stabilization occurs with that oxygen anion in the carboxylate, but not so on that free singly bonded oxygen. So again, that acid base is very, very favorable. Many orders of magnitude would be the equilibrium constant. So now we're here. This first 3-step series is what hydroxide has done. Now we throw in H+. This very irreversibly protonates the carboxylate. That's how you get to your product. That's what saponification looks like. This just happens to be intramolecular. Okay, the last one, if you tried it, is the synthesis of a T-Butyl ester with an alkene and a carboxylic acid. We're back to acidic conditions here, so the first step is something picks up an H+, last step something loses it, only plus charges along the way. In this case, the thing that gets protonated, if you try this, is the alkene. First step is the alkene picking up an H+. And if you think about Markovnikov's rule, you get the more stable carbocation. H goes on the less substituted carbon, positive charge goes on the tertiary carbon in this case. Then this sees your carboxylic acid, just using propanoic acid here, and the carbonyl oxygen will act as a nucleophile. Remember, carbonyls are the more nucleophilic spot in these acid derivatives. You form a new carbon-oxygen bond, and you have a plus charge on that oxygen. How do I get to that product right there? Well, I would love to make this pi bond a single bond. That's just a resonance contributor. And then get rid of this extra H. Oh, we're in acid conditions. Our first step was to pick up an H+. Our last step is going to be to lose it. So I'm actually going to draw out that OH bond to make this easier to see. If we used H+ to protonate this, we have some conjugate base around of whatever the acid source was. I'm just going to use a water molecule to act as a weak base that can take that H away, and in just 2 more curved arrows we can form our carbonyl and our ester linkage like so, and there is your T-Butyl ester, and you regenerated your acid catalyst. Okay, so those are just a couple of reactions that either make or use things like esters and anhydrides. They're intermediate in their reactivity of carboxylic acid derivatives, not nearly as reactive as acid chlorides, but certainly different reactions than acids. Next up, we're going to finish up by looking at amides and nitriles. There's plenty to practice after that. Thanks for watching.